Yeah, I'm going to be sharing some of the work we've been doing in modeling gene drive strategies in islands. We're starting with islands because we're trying to focus on potential field trials for now. Next slide, please. Awesome, thanks. And next slide. So I'm not going to go very deep into the mechanics, the molecular mechanics of genetic control, because it's a really deep subject, and I'm far from the best person to do the subject justice. But for the purposes of this presentation, we'll say that genetic control is any intervention based on Cas9 drives that is aimed at biasing the inheritance of certain genes that are favorable for mosquitoes not to transmit diseases or to cross their populations. For more information, I set the link for a talk by Valentino Gantz. He's a really nice guy and he really smart. The talk is in Italian, but it has subtitles. So if you want to learn about gene drives and Italian at the same time, that's the best way to go. So next slide, please. So we're focusing on Sao Tome and Principe, which is an island in the west coast of Africa. We're using this island because some of the trials our team is planning to do are there. And in our specific case in the modeling team, we're interested in modeling the spatial spread of the gene drives and developing release strategies. So in this case, every hexagon is a mosquito population scaled with size of the population. Dark blue means there's a lot of wild populations. Magenta means there's more gene drive mosquitoes, so less malaria. And this is the kind of study we're looking forward to doing. These kernels were fitted by Tomas Leon back in Cal in Berkeley. He's a really good guy, and he's also really good in modeling mosquito spread. So if you're interested in that, I can get you in touch with him. And that's it in this slide. Next slide, please. There's a plethora of questions we're interested in terms of mosquito gene drives. For the purposes of this talk, I'm going to be focusing on how does replacement compare to suppression strategies. This is replacement strategies tend to, well, we're trying to make mosquitoes still live their normal lives, but unable to transmit malaria. Well, in this case, malaria. Suppression, we try and crush their populations. We try and make them infertile or incapable of maintaining a stable population. The second question I'm going to be focusing in is how the genetic extending variation affects the mosquito gene drives. This one is, we expect mosquitoes to have some genetic variation in their genotypes, which is somewhat analogous to insecticide resistance, just because when the drive homes into a region of the genotype, there's bound to be some mutations and variations, and that could cause the gene drives to fail. Next slide, please. And next slide. So for these experiments, we start simplifying the landscape, having a panmictic populations. All the mosquitoes are in contact with each other. This is just a simplification for exploration purposes. Our model can take a spatial setting, so it's just to get started. We're using Anopheles colutzii, which are the mosquitoes that are living in that setting, and link drive. This is just the traditional Cas9 guide RNA in the same package drive. And I already mentioned the standing variation, which is one of our independent variables. And now I'm going to mention a bit about the fitness cost. This drive assumes that if a female has at least one copy of the transgene, which is the H here in the plots, she will be, if the gene drive is fully, has a full fitness cost, she will be completely sterile. If if the drive doesn't have a fitness cost, she will have its normal offspring. So this would be more like a replacement and anything in between. And we're taking as a metric the window of protection, which is we're counting the number of days in which the potentially transmitting disease transmitting mosquitoes are below 5%. So anytime that the mosquitoes can't transmit diseases is below 5%, we're counting it, and it's the blue shading in these plots. And next slide, please. I'm going to start with panel B. So the first column on the left, the 10 to the minus 6, is basically the one we saw previously. So there's almost no genetic standing variation. So on the top row, we can see the suppression strategy. It's working perfect. In the lowest row, we can see the replacement strategy. It's working perfect. The problem for suppression strategy in this case starts occurring when we increase the genetic standing variation to approximately 10 to the minus 4th. At that point, there's enough variation in the locus we're trying to home into so that some resistance can arise. And if there's resistance, those mosquitoes are fertile and they have a fitness advantage and the population bounces back. And as we go further into more genetic standing variation, it starts breaking down. The panel on the left, the panel A, is each one of those dots in the panel is one of the experiments on the left. And the darker the blue, the more days of the window of protection. So the darker the blue, the better. So there's less disease transmission. And we can see that if we increase the fitness cost, meaning that we are doing more suppression than replacement, it works fine up until 10 to the minus 4th. Over that, it starts becoming not very useful. And if we go with replacement, it works pretty much all the time. Next slide, please.
Hector, just a time warning, you have maybe about a minute.
Oh, yeah. Well, this is really brief. I didn't mention the resistant allele formation rate. This is when the drive doesn't home correctly into the locus, so some other resistance can arise, and this makes the drive even worse in suppression. So we can come back if there's questions. Next slide, please. Next slide. And I mean, I'm interested in the spatial aspect of this, of all of these interventions, so that's something we're looking forward into. And next slide. And that'll be it. Thank you. Sorry for the rushing.